You might have one who's like, well, could you do this with that? And if you have any ideas like that, feel free. Otherwise, maybe just open the link up at the top there to a few slides that I threw together this morning with some examples of things that I did with some of the sensors just this morning to kind of show what you can do. And we'll get started. So this is, and by the way, we're trying to, Ben and Sam Tomasabi and myself and newly added Fred Johnson, and anybody else who wants, Pro, Shamash, Andy, any of the regulars who want to do some kind of a casual Science Fridays kind of thing should let us know. We're trying to make these a little simpler, a little less involved, and a little shorter, so that we can get into discussion about things. But we do this each Friday, and that's the attempt. We didn't do it last Friday, but we try to do one every Friday about this time. So set your calendars and come on back. Okay, so this is Science Friday for May 29th. And we're going to talk about phone physics. If you go to slide 2 on that presentation, see kind of the screens. I'm going to talk specifically about an application for the iPhone called Firefox. I have no interest in that application other than the fact I think it's cool. And this is just kind of showing you the things you can do with it. It has the thing we're going to talk about is the raw sensor section. Accelerometers, gyroscopes, GPS, if you want, magnetometer, pressure. But there's also other things. There's acoustics, things that using the microphone, you can do analysis of audio things. You can use the sensors. An everyday life thing has an applause meter. An elevator app, which is kind of interesting. I'm not going to say any more about it, but I had not noticed that before. I think there must be a new version that has some things that I hadn't seen before, and so on. Camera type things, timers, tools, mechanics. You can take a look through that list. But on slide 3, I'm going to just talk very briefly about the gyro, the raw readout of the gyro. The phone has a 3-axis gyro that will tell you the angular velocity, how fast your phone is rotating about each of its 3 axes. And kind of conventionally with phones, with smartphones of the typical configuration, the axes are laid out like this. The x-axis is through the X and Y axis form the plane of the phone, and the Z axis is perpendicular to the plane of the phone, with the X axis passing through the short dimension and the Y axis passing through the longer dimension. And so when you talk about rotating about the X axis, you imagine that the phone was really on that X axis and then rotating so that the axis itself stays constant. The Y and Z axes will rotate will themselves change their orientation when you rotate the phone about the X axis, which doesn't change its orientation when you're doing that. And the typical convention, I should have put a right-handed thing here. The typical convention is you stick your right thumb in the plus X direction, and the fingers of your right hand will rotate in the direction that's considered a positive rotation. Same for the other axes. Point your thumb in the plus Y direction, and your fingers will curl in the direction that's considered a positive rotational velocity or rotation around that axis, and the same for the Z axis. So over at the right side of that, you see a readout. What I did was I held the phone in my hand, and I gave it a quick rotation around the x-axis, just a quick little, basically flip up down, and looking down for the z-axis. I flipped the phone kind of up down, so that it was, anyway, flipping around the x-axis quickly. flipping around the y-axis quickly, side to side, and then flipping around the z-axis quickly, kind of rotating it around that axis through the plane of the phone. And you can see in the readout that that's what I did, because there's a big flip in the green. The green is the x-axis. Angular velocity goes positive first and then negative as I rotate it backward. And then when I rotate it about the y-axis, it goes negative first and then positive. And then when I rotated it around the z-axis a little later on, it went negative first and positive. And you see little noisy things because I can't help when I rotate around one axis. I can't do it perfectly with my hand. So there's a little noise, a little rotation is also going on around some of the other axes. But in particular, you can kind of see by the fact that the green line goes positive first and then negative, that when I rotated it around the x-axis, I turned the top part of the phone toward me and then away from me, because top part of the phone coming toward me corresponds to a positive rotation around the x-axis. Whereas when I use the y-axis, evidently, if you put your thumb in the y-axis and you see that a positive rotation means left side of the phone toward me, evidently what I did was I moved the left side of the phone away from me and then back toward me to make that. And I'll let you puzzle over what I did in the z-axis. This is not very interesting, other than the fact that, just to show you, you can get a direct readout of the angular velocity of your phone using the gyro sensors. And I'll just stop there for a second if anybody has anything to say. Or it gets better. I've done the boring stuff first, so stick with it if you're not excited yet. And raise your hand if you want to come up and join in the conversation or talk about things you may have done like this. Okay, so move on to the magnetometer. The phone has, I think, probably all phones. I don't think it's very different for Androids, and I think, and maybe if somebody knows. I didn't think to look even, but somebody could look and see. There must be something, maybe even this app might be available for the Android. I assume there are apps that do the same kind of thing. There's a 3-axis magnetometer in the phone. It means it measures the components of the magnetic field. Now, in the case of the magnetic field is just a vector. And that vector has components in the x, y, and z directions that we laid out before. So what I did was I turned on the magnetometer, and you can see from the readout over there at the right that when I turned it on, the magnetic field, just the magnetic field in the room, I was just in my living room, had a positive component of about 25 microtesla, a negative Y component of 35 microtesla, and a negative Z component of like negative 15 microtesla. And what I tried to do was to rotate my phone to eliminate the X and Y components, which would leave the entire magnetic field purely in the Z direction. That means I had to orient my phone so that the magnetic field was going perpendicularly through the face of the phone. And you see, I managed to do that pretty well. After about 10 seconds or so, I pretty much eliminated the X and Y components so that the magnetic field was purely in the Z direction. And in particular, it was in the negative Z direction. So if you go back to slide 3, you'll see that negative Z axis means that the field was coming into the face of my phone and exiting out the back in the Z direction. And that's in a way, that's a compass, right? So like an advanced compass, because not only am I kind of, telling what direction the horizontal component of the magnetic field is, which is what compasses do when they tell you north and south, but it's actually telling me the direction of the field. And the place I was sitting, it turned out the magnetic field was mostly down into the earth, which it is at my latitude. The magnetic field is mostly down into the earth. It's got a northward component, but it's mostly downward. And so you can experiment with things called the dip angle. How much of the field is vertical, how much is horizontal, and so on. And one other kind of cool thing about it is, it's got a precision readout. So what I did when I finally did orient it pretty much so that there was only a negative Z component, I found that where I was sitting in my living room, it was the magnetic field was 44 microtesla. And that turns out to be a little less than a half of a Gauss, because a Gauss, the magnetic field unit called a Gauss, is 100 microtesla. It's an archaic unit that was really developed primarily to express the field of the Earth. Field of the Earth is approximately a Gauss. More approximately, it's about a half a Gauss. But near the surface of the Earth, the field is about a half a Gauss. And you can see that that's right. It's where I was sitting, it's just less than half a Gauss, 44 as opposed to 50 microtesla. One more thing about that is it's kind of fun to walk around the house and notice how much the magnetic field depends on where you are. Magnetic field inside a modern house is just all over the place because of all the electric currents and magnetic materials and things like that end up perturbing the magnetic field. If you really want to explore the field of the Earth in your vicinity, you'd better go out in an open field somewhere. Have you done anything like that, Ben? Do you know anything about, Ben, you know all sorts of stuff about house physics and magnetic fields. I don't know if you've ever looked at that kind of thing.
Sorry, buddy. I'm just servicing the 3D printer of my wife and didn't hear the lead up to that. What was the very brief summary before?
Oh, I was just wondering if we were talking about I was talking about how the magnetic field in a house varies all over the map. I was surprised. I got 20% differences, huge differences in direction, especially horizontal component of the direction, and pretty big differences in the magnitude, just depending on where I was in the house.
Oh yeah, not a lot, to be honest.
Yeah.
No, not a lot. More interested in magnetic deviations like that in aeroplanes rather than houses. But yeah.
By the way, let me welcome Beef to the stage. I went briefly, Beef, I don't know, I think you might have seen me. I went briefly into a room of yours last night. I can't even remember what it was, but I very much wanted to participate, but I couldn't, and I was afraid you would make me, so I left. But now I can't remember what it was.
I've been doing lots of stuff about Christianity being false. Was it that?
That's probably what it was. That's right. Anyway, you will see me if you keep doing rooms like whatever that. I can't remember the specific tenet, but it was a good room. I only listened very briefly. I very much wanted to stick around.
Yeah, I've been on an anti-Christian. I used to debate Muslims and try to prove to Muslims that Islam is false, but I got sick of their talking points. And honestly, the thing that kind of makes me most annoyed is that I have smart friends that should know better than to be Christians based on everything we know about the world, and they still are unpersuaded. So I'm going on a bit of a jihad against Christianity recently.
So do you know Pro? Pro might be a little more moderate than you, but I think you and Pro and I are all allies fundamentally.
Yeah.
It's the whole, I love Pro's take is the whole, that grown adults do this, right?
Yeah.
I like that take. Anyway, welcome aboard.
Thank you.
Any other comments on magnetometers or fun things you can imagine doing with a magnetometer? Okay, well, let's move on. moving on into the good stuff here pretty soon. In fact, I guess this is the good stuff, right? Let's see. Shoot. I just realized the next slide says magnetometer, but it should say pressure sensor. And now it does if you refresh, if you haven't. Anyway, the pressure sensor. This is pretty cool, I think. The fact that your phone can very accurately detect the way atmospheric pressure changes over even 1 foot of elevation. If you raise and lower your phone by 1 foot, it will very clearly show you that the pressure is higher, 1 foot lower than it is 1 foot higher. And so I've just got 2 screenshots here. The first one, the first graph, is what you see if you just lay the phone. I just placed the phone on a high countertop. We have 45 3/4 inches, 1.16 meters. I just placed it on the countertop and let it record the pressure. And you can see that the pressure fluctuates. It's interesting, I've done this before, and if you let it go for quite a few minutes, you will see whether the pressure is systematically increasing or decreasing. And you may know that increasing pressure is usually correlated with weather getting better, clearer, storms passing, etc. Whereas falling pressure is just the opposite. So you really can, with your phone, just set on a countertop, reading for a few minutes, you can find out whether the atmospheric pressure is increasing in your vicinity or decreasing. And I don't think I took it long enough here to reliably say that what you see there is an increasing trend, because it does kind of fluctuate, especially if you're inside a house, if there's any kind of, air conditioning system or anything like that, any kind of ventilation, you might see pressure variations. Notice that those variations are on the order of 1/100th of a so-called hectopascal. Now, hectopascal is 100 Pascal, but and I'm not going to worry too much about that. But just to notice that the variations here are in the 5th digit. Almost the 6th digit, because that number is close to 1,000, right? All those numbers, 970, are close to 1,000. So in some sense, that variation is really at the 1 part in 10 to the 6th level. Is that right? 1 part in 10 to the 6th. I think that's right. Very small variations. And to really drive that home, on the lower graph, what I did was I let the phone, the pressure record for 10 seconds, and then I lowered it to the floor. Notice that the scale on that second graph has a range of about 0.1 Pascal, whereas the range of the other one was about 0.02 Pascal. I was getting little fluctuations there. But you can see very clearly when I lowered it to the floor that the pressure definitely jumped by a little more than a tenth of a hectopascal. Sorry, I think I was saying Pascal before. A clear jump associated with the phone being lowered to the floor. And then you can go into precision mode and actually get the readouts there. So the top one is a kind of a later readout. I didn't do these at the same time, but when I did the readout later on, I got a difference. I got the 970.783 at the floor and 970.669 on the counter. And so you can get what's called the pressure gradient, the rate at which the pressure is changing with altitude, by taking the difference in those two pressures, dividing by the altitude difference. And I'm showing it there. What I end up getting is 9.8 Pascal per meter. Now, what's a Pascal? A Pascal technically, formally is a Newton per square meter. It's the metric unit of pressure. to be compared with pounds per square inch. Metric unit of force is newtons. Metric unit of area is square meters rather than square inches. And so it's the metric unit of pressure. And the best way to consider that 9.8 Pascal per meter is to compare it with atmospheric pressure, which is 100,000 Pascal. If you notice that 1 atmosphere is 10 to the 5th Pascal, and that the pressure here changed by about 10 Pascal per meter, that means that the pressure gradient is equivalent to going through one atmosphere of pressure in about 10 to the 4th meters. If I multiply that pressure gradient by 10 to the 4th meters, I get about 1 atmosphere. And that means that near sea level...
Which is the thickness of the atmosphere, right? So this is the effective thickness of 1,000 kilometers.
Yeah, so that's exactly where I was going. That's right, exactly. So it's effectively what we learn here is that if that pressure gradient were maintained as I rose by 10 kilometers, I would find that I was down to 0 pressure. And so it's exactly what you were saying, Shamash. It's kind of effectively the thickness of the atmosphere. If the atmosphere were a constant density blanket, it would be about 10 kilometers tall. Since it's not, it turns out that the math actually says that it decreases exponentially. That 10 kilometers turns into what's called the scale height. At an altitude of 10 kilometers, the pressure has gone down by about a factor of 2.7. Where does that come from? Shamash can tell us where that 2.7 comes from.
Euler's number.
That is Euler's number. That's right. So we could talk about exponential processes another time, but a scientist would look at something like that and see right away that what that's telling you is what's called the scale height. Every time you go up by 10 kilometers, the pressure is going to decrease by about 1 over E, 1 over Euler's number, which is 2.73. Isn't that fun? Yeah. So anyway, that's kind of a fun thing, and I do think that it's pretty amazing. You can both be kind of a weatherman with your phone. You can just let it record the pressure. You can see whether the pressure is rising or falling, and you can get very accurate. Now, I think the absolute pressure you measure may not be quite as accurate as is indicated, but the pressure differences that you get are, if it, in this case, I really am measuring a pressure gradient of probably within 1% or 2 of that 9.8 Pascal per meter. I'm just going to call it 10 Pascal per meter because that's perfectly accurate enough. And that's what it always is, by the way. The pressure gradient near the surface of the Earth is always about 10 Pascal per meter, unless maybe you're in a tornado or something like that. Probably has aeronautical applications too. We got pilots in the room who might be thinking, ooh, or they might not. Let's see. We got some folks. I see some raised hands. Sorry, I haven't been paying much attention. We'll see.
My sound isn't that awful. I don't know if it's time for questions or...
Yeah, no, it's always time for questions.
All right. So I'm skipping ahead in your thing here. I'm looking at the accelerometer as well.
Yeah,
I'm trying to think about what exactly, like right now I'm on the treadmill. So is it the accelerometer that's helping it know that I'm going like up and down and I'm bouncing around on this thing? Because my arms aren't moving really on the treadmill. I'm holding my hand and I'm looking at my steps and it knows I'm taking the steps.
Right. Yeah, that's right. The step counter surely relies on the accelerometer to count steps. And I don't know the algorithm for that. It has to somehow distinguish steps from just kind of gradual acceleration. It's looking for something that looks like an impact, right?
Well, I know my hand is like the only thing it's doing is it's slightly going up and down when I bounce. Like I'm trying to hold it as still as I can. And I was thinking about that while I look at it. Like I'm not really moving it. Maybe I am side to side slightly, but it's more up and down. And it has to know that there's some kind of. Does it like know it's a pattern? So it's like, oh, he's walking.
Yeah, I've often wondered the problem I've found when I try to, when you try to fake your steps, right? You haven't quite got your 10,000 steps in. It's time for bed.
Yeah.
You just like move your hands
Swing
up
your
and
arms
down
more.
with the phone.
Yeah. Exactly. Yeah.
And I don't know how you can never. I can never tell immediately because it seems like it kind of counts for a while and then every once in a while updates. So I never can really tell whether it's counting steps or not when I do that. But I assume that it must have something to at least try to distinguish just, kind of moving your body around, shifting in your chair from taking a step. And some of that might be vertical, right. Looking at vertical rather than horizontal. I don't know what the algorithm is.
I think a large part of it's taking sorry to interrupt, is taking a Fourier decomposition of it and then filtering things by in frequency space.
That makes sense too. That's right. Okay. All right. Okay. So if anybody does actually want to have a comment or question, that's fine.
So
we don't take music.
Is that walking on a treadmill is the same as walking down the street from an accelerometer's point of view?
Are you raising the whole do you do work on an inclined treadmill question?
Well,
is that where you're going?
That's probably related.
I'm on a flat treadmill.
But no, it's just, but just the idea, like, what it senses, is it the same thing?
Yeah. So that, in other words, if the treadmill was just horizontal, would it be exactly the same as walking down the street? And Einstein has an answer for you.
Right. But the phone can also consult its GPS.
That's true. I always forget that. In fact, one of the fun things is this: there's a deal in Firefox. Excuse me. Yeah, thank you. I should have known, right? The problem is on Club Deck, I can't look at the number of friends. Let's see who we got. Well, we're going to give this a try anyway. I'm bringing Benjamin up, so it's not like all bets aren't off, right? Let's see, Benjamin, are you coming up? You are up, okay.
Morning.
Morning, Benjamin. And what are you up to? See, did I invite?
I was just at the airport. My basic airport noise monitoring.
Okay, well, this
participants.
Firefox has acoustic sensors too, so maybe get yourself a Firefox.
This is like a
See
cell
if they've
phone,
already done
right?
it.
Is it a cell phone?
Yeah.
Yeah.
What, you're scoffing at cell phones now? Now that you've become an academic?
Yeah. Calibration is an issue.
When did these start having all of this stuff in it? Because I remember back when my phone started being able to do stuff. I wasn't looking it up, but I remember different like games on your phone, different like even the pedometer thing. Like it couldn't do this that long ago. I mean, maybe like 10 years ago it could, but I don't even know if it was 10 years ago that I had a step thing that worked on my phone. Of course, being an Android person, it's probably different, but I know iPhone way back. When I say way back, I mean like 15 years ago or so. Could do, kind of know like when you flipped it. You know what I'm saying? If you flipped your phone, it knew that. That was the first thing I remember knowing. But it seems more and more of this stuff has got packed on.
Yeah, and it never gets any fanfare, right? I mean, it is amazing the things that are in the phone.
Right.
And they just, nobody says,
I never remember Tim Cook or any of these. Yeah, I never remember anyone saying that at the Geek Squad when they reveal it. Maybe they did, and everybody was just like, it was on the handout or something. So.
Yeah.
These sensors might have got added even earlier for other reasons. Like I know that back in the day of spinning hard drives, accelerometers got put in So like if you dropped a laptop, it would sense the 0G and lift the head off the drive
All
before it
right.
hit the ground. So I think some of these sensors just started getting incorporated into microelectronics for various reasons, and it's at some point it's probably like, well, why not? Why not just turn this into a tricorder?
Yeah, it's funny. I was on this train trip going to and from Chicago recently, and at some point I wanted to know how fast the train was going because it felt like we were going 1,000,000 miles per hour. I knew we weren't because we don't have high speed trains, but the tracks are so bad in this country that when the train goes as fast as it does, which it turns out is 90 miles an hour, Amtrak's go 90 miles an hour. Who knew that? It is a rough ride, but I wanted to know how fast we were going because I knew we were going pretty fast for given how bad the tracks are, and I was thinking, well, is there any app that does that? And I was like, of course there should be something that uses GPS, and so of course you go to Waze or any nav program, Google Maps. You have to set in a destination with Google Maps, but in Waze you can just go. Open up Waze and it'll just tell you how fast you're moving. In Google Maps, you have to put a destination in, and then it constantly thinks you're on a road. So it's constantly telling you you're going 90 miles an hour, but the speed limit here is 25. It's got this big red flag up. So that's kind of fun. But I was mentioning it in particular because one of the things on the Firefox app is a velocity. Is a thing that'll tell you how fast your elevator is going. Now, how do you suppose that works? Because there are lots of ways it could work.
Well, accelerometers to get you going, and maybe, but they're noisy. They drift pretty fast, and then, but yeah,
The, the
pressure.
floor the floor the floor length is standard at 3 meters or something, so they calculate the duration and they divide.
You're saying integrate the acceleration, Shamash? Is that what you're saying, basically?
Well, the acceleration phase is the accelerometer, as Hero said, but then
Right.
the constant speed phase, it should be just assuming a standard height of some sort and then dividing. So
I
they
think
count
Andy got
time.
it. I think Andy got it right. Just all you have to do is just read the rate of change of pressure.
Did Andy say that? I didn't. Somehow I didn't hear
Andy
it that
said
way.
that. Yeah, I wanted to
Pressure.
make sure that-
Yeah, and that's
Did
right.
Andy say
That's,
change of pressure? I thought he said accelerometer.
I thought he did
it's
too, but
to get you started, but to really keep track, pressure I think would be the same thing. GPS height too, but in an elevator you might not be getting great GPS.
yeah, no, that's right. So the GPS is going to give you a value, but it's going to be really shitty. The accelerometer will certainly give you a value too, but that's not what they use. What they use is the pressure. They use the pressure to tell you how fast the pressure, the rate at which the pressure is reducing, which is kind of weird because it does mean that they have to kind of assume. Well, I guess that's right. I guess they can tell both what altitude you're at, and knowing what altitude you're at, they then know what the pressure gradient at that altitude is, and then they can use the rate at which the pressure is changing to tell you how fast you're moving. So it's really, I don't know that that's how they do it, but I do know that they use the pressure sensor to determine the velocity of the elevator, which is just kind of wild.
There's no VSI kind of instrument in the phone, I guess.
So what's that?
So on an airplane, you have your altimeter, which is pressure, like what you're talking about, but you also have a vertical speed indicator, which is like it's like an altimeter, but it's you have a little chamber, and then you have a little hole in it, and it's the rate at which the air goes in and out of that hole. It's like a calibrated leak, and so it's basically designed to measure the rate at which you're going up, or yeah, to display the rate you're going up, and it reacts pretty quickly too. It's got a little bit of a lag.
So it is sensing the pressure gradient, basically the rate at
But
which the pressure is changing.
It requires a cavity,
Huh.
because it's like it's measuring the difference between the ambient and what and what's in the cavity, and because it's got a calibrated leak, it takes a little time for the cavity to catch up with the ambient. So if you're moving, you can always measure that air going in and out.
Interesting. Yeah, it's kind of wild, just this stuff that goes on behind the scenes without, just the stuff that is taken for granted. It just gets crazier and crazier all the time. Well, let's move on to the accelerometer. This is probably my favorite sensor in the whole thing. The accelerometer is the way the phone discovers how fast its velocity is changing. And one of the best things about it is it knows what Einstein, it understands what Einstein called the most wonderful thought of his lifetime, or something like that, and that is that a falling person can't feel gravity. There's no gravity when you're falling. It knows in particular, and I want to show that here. I'll just show you a couple things I did with it, and then we can talk about it. First of all, I took the accelerometer, which is a 3-axis accelerometer. It tells you how much, what component of the current acceleration is in the x and the y and the z direction, as we discussed on slide 3. And so I just took the phone, put it face up on a table, and recorded for a couple of seconds the acceleration. There's a couple things to notice about this. First, that both the x and the y accelerations are sinusoidally varying. It's going up and down, and they're not varying around 0. That's another thing to notice. They're varying with a period of, or the frequency of, about 4.5 cycles per second. Acceleration, very small up and down, but noticeable and definitely regular, with a very definite frequency of about 4.5 cycles per second. Not, as I say, oscillating around 0, not cycling around 0, but close to 0. Within 0.1 of 0, basically. Whereas the Z accelerometer is just shy of 9.8 meters per second squared. The phone, when I set it on a surface, thinks it is accelerating upward at 9.8 meters per second squared. And that's weird, because that's the rate at which a rock accelerates toward the Earth when it is released. But of course, if you think about that, the phone doesn't know if it's on Earth or in a rocket ship, which is accelerating in order to simulate Earth's gravity. Because if you had a rocket ship accelerating in one direction at 9.8 meters per second squared, and you put the phone on the, quote, floor of that rocket ship, it would correctly determine that rocket ship is accelerating upward at 9.8 meters per second squared. And of course, this makes contact with my favorite topic, which is simply the fact that in relativity, the surface of the Earth is accelerating upward in an absolute sense. Acceleration, unlike velocity, is a thing that has an absolute value. Objects have accelerations. They don't have velocity, but they do have acceleration. And an accelerometer can measure the acceleration of an object. It doesn't need, unlike velocity, which always needs to be referred to something else that's considered to be at rest. All you can do is measure your velocity relative to something that you may or may not want to consider to be at rest. Whereas acceleration, you don't need that. Accelerometer is a completely self-contained device which tells you directly the absolute acceleration of the object that it's attached to. In this case, the phone, when you set the phone on a horizontal surface, it is absolutely accelerating upward at 9.8 meters per second squared. And that raises all sorts of questions, which I'd love to get into. But maybe we'll just wait to get into those questions for a little bit. But there are a couple things. So that's the Z. But what's going on with X and Y? I don't know. But I'll just point out there's a couple of weird things about X and Y. The fact that there is a sinusoidal oscillation, the fact that it has a definite frequency, low frequency, and the fact that it's not oscillating around zero. What does anybody make of all those things?
Wait, I missed that part of it. You're saying that if you set your phone on the table, the Z value has 9.8 and the X and Y are not quite at zero and moving around?
Yeah, they're in this case, both of them, for whatever reason, happen to be oscillating around some negative value. So that's weird. Maybe that's weird. Maybe it's not. The fact that they're oscillating with a definite frequency of about 4.5 cycles per second is weird. It's a small vibration, small up and down, or small back and forth, whatever you want to call it. And I'll just be honest, I don't know. It's very clear that the phone was doing that. I think that's a very clear signal. And it was not an earthquake. There was no earthquake happening.
You have clothes in your dryer?
We didn't have clothes in the dryer. There was no washing machine moving. But I do kind of assume that's where you're going as well, that there's some mechanical device that is, making the house move about 4.5 times per second back and forth at a very low amplitude that I certainly don't detect myself.
Or could you is it close enough to zero that that's just what zero is? Like they could have some bias in them.
So you're addressing not the vibration, but just the fact that it's not around zero, right?
The vibration could come from some sort of sampling thing.
Oh. Now, I'm not sure how that would
9.8,
work.
Does the 9.8 also have, if you were to look at it closely, is it also vibrating or something?
That's a good point, and it's hard to look at it closely because the scale is a little bit. Well, actually, is it? Let's see. What do we have? We have a range of about in the 2. We've got a range of about 0.1 meters per second
I feel like there
squared.
should be a tear button.
Yeah,
but that zeroes it out.
Well, it's funny. Yeah, it's funny because I don't see that. I mean, the oscillation amplitude, the peak to peak amplitude is about 0.1 in both of those. And you would definitely see that noise in the Z. The Z is noisy, but it's not noisy at 4.5 cycles per second. So that's another weird thing.
Well, can you tilt the camera 90 degrees and then set it and read it that way? And then
I
The X or
can.
the Y will be at 9.8 and the.
Yes, you can do that, and I do kind of assume that the offset might just be an error, might be a bias in the sensor itself, but it also might just be that the phone wasn't exactly level, so it was sensing some constant, part of the acceleration due to gravity, if you want.
That the angle it's at is just between whatever sampling, it's kind of going back and forth between them. There's there could be like a resolution. Well, I'm just guessing.
It might be. It's funny. It's funny to me that the noise in the Z just looks like noise, even though it's kind of the same. The range of the y-axis there is kind of the same range, but in the Z it just looks like noise. Whereas in the X and Y, it's a very monochromatic, single 4.5 cycles per second with a little noise on top of that. So that's weird. I don't know what to make of that. But at any rate, the main point, of course, is the fact that when an object is just sitting on the ground, an accelerometer will tell you that it's accelerating upward. Plus maybe little other artifacts as we see there. And to really explore that a little more, what I did was I took the phone. It has a nice timed data collection thing, so you can have it wait for a while if you want to collect some data without screwing up the phone by pushing the start button. You can have it delay the start of its collection. You can have it collect for a certain amount of time. So I had it just collect for 1 second, and then I waited and I was holding the phone in my hand, and as soon as it started taking data, I threw the phone upward, making sure that it would land on my sofa, which it did. After the end of the 1 second, I threw it up in the air, so it was in the air for at least the last half second of that period. And so you'll see kind of an interesting thing there. You'll notice, first of all, that the Z accelerometer was once again started out at about plus 10 meters per second squared. The X and Y closer to 0, but I was holding it in my hand, so I wasn't holding it perfectly steady, and I was anticipating, of course, desiring to throw it up in the air in a half a second. So it's a little noisy there, but then you can see me throwing it up. You can see that the Z acceleration goes up to 20, 30, 40 meters per second squared as I just kind of very quickly tossed it upward. There's also a little noise in the X and Y at the same time. And then once it was in the air, notice the noise goes away. So that's kind of an interesting thing, at least at this scale. There's no noise. And the Z component looks like it just goes to 0. Now I'm guessing on a higher scale, you'd see that it was doing something like the X and Y are doing. Notice the X and Y don't go to 0, but they do go to a very smooth kind of sinusoidal shape. So there's another thing to think about. What happens to the phone? I was naively, of course, just expecting all of the accelerations to go to 0. When I threw that phone, all of the accelerations should go to 0, because the absolute acceleration of an object that is in free fall is 0. So why didn't it?
Was there a rotation?
Of course, I couldn't keep it from rotating. Why do you ask?
Well, it seems like that would be a hard thing to prevent. And if it was rotating, there'd be... Well, I mean, what would that do?
No, I think you allowed me to cow you a little bit. You're absolutely on what I'm sure is the answer for why the X and Y look like they do. If you think about, because we don't know where the accelerometer is in the phone, but unless it is right at the center of mass, it's going to be moving around in a kind of a circular motion somehow around the center of mass while the phone is falling, because I couldn't keep it from rotating. And if it rotates, if the accelerometer itself is rotating around the center of mass, then the components shown by the accelerometer will, of course, oscillate sinusoidally with the rotation period of the phone. So I'm pretty sure that is what's going on in both the X and the Y direction. And notice the X is clearly not oscillating around 0. That's because the phone not only is rotating, but it no longer, even though I was holding it kind of face up before I threw it, when I threw it, it just kind of went into a tumble. So, but at any rate, you can still see the nice fact that, to at least first order of magnitude, the acceleration, the fundamental acceleration of the phone, goes away once I've thrown it up. Part of that's probably on the way up. It might be on the way down. By the end of that, I didn't throw it up very, very hard. It would only be in the air for a second, probably. So whether it's going up or down, you see almost no acceleration there. Anyway, that's fun. I love playing with the accelerometer. Okay, one last thing. This is not in the fundamental sensor thing. It also, if you give it access to your microphone, it can do all sorts of things with sound. And you can look back at the second slide to see the selection of things it does. But one of the things is a sonogram like this, where it's telling you the frequency content of the sound as a function of time. So time is progressing upward here. And what I did was I am a really bad, I have lost the ability to whistle in my doddering seniorhood here. But I can still go like, oh, I'm kind of whistling now. So I can still do that. And so what I did was I whistled a major triad. I did something like, that's a major triad musically. And it starts with a root, goes up to the major third, and then a fifth, and then the octave. And so if you look at the white bands in there, you'll see that the predominant frequency starts at around 1,000 maybe hertz, and then goes up, and then the final one is about 2,000 hertz, maybe a little more than 2,000 hertz. The first one was probably a little more than 1,000 hertz. So those white bands are just kind of showing you the frequencies of a major triad. Nothing very exciting here, but the audio stuff is very cool. It's got lots of, and this isn't, it's fundamentally just using the microphone. But what the app does with the microphone then is all these Fourier analyses of the spectrum coming in, kind of typical things you do. So it's not, as I say, it's not really just you already have apps that make fundamental use of that sensor. They're just called, voice recorders and Clubhouse and all of those things. So it's probably the one sensor you're most familiar with in the phone, but it gives you access to these analysis tools. All right. Well, anyway, so that's Science Friday. We can talk more about that. We can talk about gravity, or we can talk about, Sam always wants, Sam these days comes in and talks about drugs. By the way, hi, Sam.
Hi. Sorry I had to back out today, but hopefully next week we're going to discuss generic drugs. But thank you very much for stepping in.
Yeah. Well, let's see. You've got CM coming up here.
Good morning, everyone.
Hey, CM.
Hey, Benjamin. We won't discuss this now, but I have good news for you if you're there.
Benjamin's probably. Yeah.
Hey, John, I missed the first part of this. This thing in your slides, what's it called?
The app?
Phone? Yeah, is this talking about, is this revealing the underlying sort of whatever API access to your phone? Is this iPhone specific, or is this a generic thing?
Yeah, well, this particular app is I don't know, actually. I mean, this app may be available for Android. I'm not sure. I notice in particular that it's got a thing called in the raw sensors, it has light. And for whatever reason, it's grayed out. I don't know. I thought that the iPhone did. Well, I know the iPhone has some kind of a light sensor, right? Because it knows when it's dark. So I don't know why it is that we can't get, for whatever reason, I can't, at least on my version of it, get raw data from the light sensor. And I don't know if that means that on the Android you can, or if it's just my iPhone. So I don't really know. It doesn't give you, you can, in all these raw sensor modes, you can gather data and then output it to a spreadsheet, right? So I don't know if that's what you were getting at, but it doesn't give you something that you can plug into another program, if that's what you're asking.
No. I guess I was wondering if this was exposing what the iPhone made available or some fraction of it. I don't know. I'm just curious. I just missed I missed the
Yeah.
setup. So
Well, I probably didn't say whatever it is that you're interested because I probably don't know. I mean, I haven't really looked. In fact, just in throwing this together this morning, as I did say earlier, I noticed that there are some new elements of the menu that I don't think used to be there. So the app must have updated recently with new things, but I don't think most of the things beyond the raw sensor section really are, analyses using the raw sensor. They're not just the raw sensor data. And I just like the things you can do just by looking at the raw pressure and accelerometer especially.
but how is it? So there's all the gyros in there, right?
You're breaking up a little.
I never quite understood what is a gyro just a sort of arrangement of accelerometers?
I wondered that
Or
myself, and I put a link to something that talks about that. But because, I wondered about it while I was throwing this together, I haven't actually looked at that link. But if you look on slide 3, there's a link that I want to go to that at least starts to talk about the question you're asking. I don't know if I don't think, I mean, you pilots should understand this better. It might just be, different accelerometers. Maybe can you just do that maybe with the accelerometer if it's not? No, I don't know. I honestly don't know how that works. I don't think they're, laser, what is it? Laser gyros.
Ring laser gyros.
Ring laser gyros, yeah. But Ben, you know about this stuff.
In the iPhone, they're Hall probe accelerometers, just simple solid state accelerometers, I think.
So
I think what they do is they still have little tiny masses on a little tiny, I think it's just a little tiny mass on a bent piece of metal, and then they measure the capacitance or something. I think that's what happens on an iPhone.
Oh.
I'm not sure, 100%.
Yeah, well, it may be that
Google,
I'm hoping that
search,
link.
So. It's basically on chip on an iPhone. They're kind of almost in silicon. The way that it does accelerometers. And I say it's Hall probe. I'm not sure it is Hall probe. I don't know how it detects the movement of the mass. But again, it's only a Google search away.
Well, I do have that link, which I intended. It looked like it at least was, at least started to answer the question. But maybe I don't know how much it does. Oh, actually, now that I look at it, I don't think it does at all. But just talks about what they use it for. At any rate, it's an intro. There may be something in that article that will point to, we could, of course, just ask Claude. I was reading, who was it? Somebody, Rick Sanchez sent me a link to a new paper in Science talking about sycophantic AI. Do you know what sycophantic is? Has anybody heard that term?
Yeah, I mean, it's all that. It's all the chat versions of the AI. They're all very much trying to please you. That is the clues in the name. They want to keep chatting. It's casual. It's a two-way thing, and it wants to perpetuate because that's how they make money.
So I hadn't heard it that referred to that thing that we've all experienced. I hadn't heard it referred to as sycophantic AI, but it was talking specifically about the social dangers of that. Just the whole closed epistemic loop thing. You ask it a question, it wants to please you, it detects kind of what answer you're looking for.
What you can't verify.
Yeah.
Just don't even ask what you can't verify.
Well, but the problem is
the result. Don't ask it.
The problem is the people that it will most quickly damage won't do that. And I've seen this in the flat Earth community in spades. Flat Earthers now, Alan and Shane in particular, are just vibe coding this crazy shit that looks amazing, gives you all this ability to adjust parameters and get really beautiful graphics, and it's all just horseshit. But it looks so wonderful, and they're completely, of course, captivated because they just tell it what they want it to show, and it does. And of course, we've
Yeah,
got
that's so
them all
what it's very
asking.
good for is engineering things properly, stage by stage. You build a verifiable layer. You use the agent to help you do that. You build another layer on top. So I don't use chat for anything anymore. Not even the most simple query. I haven't used Claude Chat for a long time. I do everything in code now. And if that means I'm just asking the simplest question, sure, it's just the same as chat. But the moment there's anything to be remembered, any facts to write down, it's writing it out to files or a database or just something. And we're starting, and I check what it's written down. So we're like planning our trip to San Jose, for example, and I'll give an agent the job of finding all the accommodation that's available, because the last thing you want to do is go on booking.com and find all the shit that's not available. So it goes off and literally clicks through in Chrome and finds all the stuff that is available, but it puts that in human readable files. So we can look at those files and check that it makes sense. And then you go a layer further onto that, and then you keep building. If you verify at each layer, you can do amazing things. It's the same as just building software. But if you just ask a question, it's just going to do its very best to please you, which is dumb.
Go ahead, Fleming.
Hey, how you doing, guys? I'm a scientist as well. I'm an epidemiologist. I want to say that, what scares me is the fact that I know you guys were talking about something other than what I'm about to bring up, but what scares me is we know about, researchers who uncovered viruses that was frozen 30,000 years. And so when you're talking about politics and things like that, a lot of people don't. I'm sorry. Like, a lot of people from the Republican Party don't believe that there's greenhouse gases that are affecting our planet. And so you're looking at viruses that are going to be uncovered because of the fact that it's warmer and they're going to be unfrozen, and we have no immunity against that. And so this is, from the epidemiology community, this is what is going to scare us. Is the unknown. And so, what do people that have questions about that? What do you think about that? That's going to happen.
So this is totally out of I fancied myself an amateur epidemiologist when the COVID thing. I was compiling things and making predictions, all of which turned out to be totally wrong. But at any rate, I know nothing about biology and epidemiology. Sam is, in that field, and I wasn't aware. Is that true that ancient viruses can become a problem?
It is a big fear, yeah, that ancient viruses are buried deep in glaciers and in Arctic and Antarctic ice. And as global warming are melting those ice sheets, those viruses and bacteria are getting released. And Fleming is right, is that the theory is, and the theory is kind of based a little bit on fact, because when they go down and take ice bores, they do see species they're not familiar with, and so yeah, that's a big fear, that those things, as the ice melts, they're gonna get released, and we don't have any immunity to them because they have been out of the ecology for so long that really no species has any immunity to them. And so this is going to be like a basically a global ecological disaster if the worst scenario comes to.
So that is really interesting. I mean, I didn't know any of that, but I'm wondering. I mean, it seems like there would have, presumably, this kind of thing would have happened in the past, the deep dark past, with glaciation, etc. Is there any evidence that that's been responsible for extinctions or anything like that?
No, there isn't. Yeah.
And there's no
But it's
evidence.
just I mean, it's just that the viruses and bacteria who were at the time, they just got trapped in the ice, but then the rest of them evolved and became something else over the 100,000 years.
Right.
And so now these old ones are they're the ones that we didn't evolve with them and they didn't evolve with us. And so it's going to be a
Sam,
huge shock.
with the
if I can,
bacteria though, presumably the bacteria is much less of a concern. Wouldn't you have thought that the older bacteria would just be a simple penicillin job or something? Or is that not necessarily the case?
That's not necessarily the case because our antibiotics are designed for the current bacterial metabolism. And so if those guys are doing something else,
But there's a lot of
that
classes of
is
antibiotics now, and we don't just
yeah.
attack. We don't. They're not just anti-metabolites. We have fluoroquinolones and we have nitrofurans and we have
No.
beta-lactams
As
and
in, not that kind of anti-metabolism, but so every kind of antibiotic that it shuts down one or two pathways in the biochemistry of the bacterium,
yeah, or just
right?
physically cleaves its cell wall or whatever. They all do different things, right?
Yeah.
Fleming's trying to get back in here too.
Go ahead, Fleming.
no, I just want to say like we have no immunity to what the brother was saying, Sam was saying. We have no immunity. Siberians uncovered a 30,000-year-old virus in Siberia, and the thing is that we have no immunity to that. So imagine millions of viruses that are frozen in a glacier and we are getting exposed. And South Florida is going to get exposed, because we saw the thing that where if the glaciers melt, South Florida is going to be underwater. Florida's going to be underwater, and so, or at least part of it. And the thing is that you're going to be exposed to viruses that were frozen for millions of years. We have no immunity to that. So what are you going to do? And so this is. I'm sorry, brother. Go ahead.
No, that's fine. I didn't mean to to cut you off. But I am. You mentioned this one virus. Is this how? Are there examples? Are there other examples of viruses, ancient viruses that they have found? And what do they? I don't know. What do you do? Seems like I don't even know how you find them, but you'd want to handle them with care, etc.
The thing is that I'm not a virologist, but I know that there were samples that were taken, and the virus was a long virus, and it was 30,000 years old in Siberia. I don't know if this is a Russian government or whatnot, but the thing is that they uncovered that. They uncovered that. And the thing is that they were saying that it lived. When they thawed it out, it lived. And it's like, wow. Imagine what happens when, you have political parties saying like, well, greenhouse gases doesn't exist. And the whole world heats up and the glaciers melt. Now you're having viruses that were frozen millions of years exposed to the human population. That's crazy.
Yeah, so I'm just reading a little bit about ancient viruses. But suffice it to say, it's not a topic I even had thought to think about before. That'd be fun to know more. I mean, I honestly don't know. I'm kind of taking your word for. I get certainly the potential danger. I wonder. It's surprising to me that I haven't read some kind of an alarmist piece about it, because it sounds like the kind of thing that somebody wanting to go that way would kind of easily be able to raise your fears over. So it's surprising to me that.
Well, it's
that
because it hasn't
done.
happened yet.
You
Right?
think that's all it is, Sam?
Yeah, that we don't have any case of a diseased individual that we can link to one of these ancient viruses. So as of now, it is not a real danger. It's a potential danger. because we also don't know, when they get released, what do they do, right?
Yeah.
We don't know how they're going to affect our bodies. I mean, it may be that all these ancient viruses somehow they can't infect us, right? So that could also be something. So what Fleming and I are talking about is the worst case scenario,
Yeah.
which may or may not come to pass.
Well, I see here it says, I mean, that there's more than one of these. Obviously, there's quite a few, but they've been studied, and so far they infect only single-celled organisms.
Right.
I don't know why
Yeah,
that would be.
that's what I'm
I don't
saying.
know what
Well,
that means.
because they evolved when we only had single cell organisms.
Well, but that's not true, right? If they're 30,000, 40,000 years old.
Yeah, that's true.
Yeah.
Yeah, but why would we forget? Yeah, I don't know. It's all speculation until you get one of them and sequence it and do what you need to do to work out whether it's a threat. You're definitely talking about the worst case. It could be that they're all.
Yeah.
It could be they're all nothing to our modern immune systems. It could be that they're all a threat. It's likely to be something in the middle.
Yeah,
And
we
then the
don't
chances,
know. Yeah.
we have no clue. And then if they are a threat, we don't know whether we're able to sequence them and use existing antivirals, or we quickly produce new ones. Although that's not going to help for years, as you know, Sam. So it's all just a lot of don't know. It could be anything from a nothing burger to a disaster. It sounds a bit like the Millennium
Yeah.
Bug to me. Sounds a bit like the whole,
Yeah.
clocks messing up all the computers bug thing.
Well, it's something that, COVID could have been that, right? COVID, or if you guys have read Station 11, the book, it's about a virus that takes 48 hours to incubate and 4 hours to kill you after you show signs, right? So could be any of those.
It seems to me like what we need are some new sensors for our phones, CRISPR, some kind of sequencer, some kind of DNA sequencer or something.
Yeah. So when you throw the phone up in the air, it sequences.
I think Io is working on that.
I'll bet he is. It sounds like the kind of thing, right?
I was gonna be ask the virus, are you a good virus or are you a bad virus? And then right? You're gonna.
Yeah, well, I was trying to bring it full circle here, but probably lost cause.
That was a diversion.
Weak.
So sorry about that.
No, it's fine. I'm going to have to close this down. My wife and I have COVID booster appointments coming up, so we're going to go do that later on today.
Or leave it running, John, if you don't mind, and we'll just keep chatting for half an hour.
Yeah, I think maybe can we open another room so this will stay on replay as
clean, exactly.
as this thing.
Yeah, I'll go ahead and open a new one.
An after party. Good.
Cool.
Yeah.
I'll see you there.
Okay. Yeah. All right. So I'm gonna just close this room down unceremoniously in a few moments and look for Sam's room, Scientific Discourse House after party thing, and we'll talk to